In this video, let's discuss about the mass and weight here, get to know the difference. Now, as you know, the mass and weight are a distinct term in science, but as we speak literally, we assume that both of the mass and weight sometimes are just like the same. So I just want to bring you an example of how these two terms can be really confusing. So if you say 1 kg of rice, does it refers to the mass or does it refer to the weight here? Or does it refers to both here? So I'll get you to understand this particular term here of why these things are confusing, and we use these all terms in our daily basis here. So to understand this, let's get into the definitions here, get to know the difference here. Alright, so mass is the amount of substance contained in a body or an object. So it talks about how many atoms or how many molecules are present in a particular body or an object here. So take for example this guy here, not so much of a drawing, but we know that we are all made up of atoms, and so how many atoms are present in this guy here will define the mass here, as the definition says here. Alright, so take for example a block of sugar here, and we know that sugars are made up of sucrose molecules. So how many sucrose molecules, the amount of sucrose molecule present in this particular block of sugar will define the mass here. So mass usually talks about the number of atoms. We'll get to study the properties here, but first let's take a look at the weight here. What actually is the weight here? Alright, so weight is the force acting on the object due to gravity here. Alright, so what you want to know here is that weight is a type of force, and not any other type of force, but the gravitational force we are talking about here, in which the weight is induced here. So we know that each and every object on this earth experiences this gravitational force, which pulls the object or substance down toward the earth in this vertical direction. And what actually weight here is that how much force, so let me just write down here, how much of this force, means the gravitational force, is exerted on the body. Let me just write down the full sentence here. On the body is what we call it the weight here. So weight is nothing but the force in which the gravitational force acts on it. Alright, so we'll come back to the definition here, but let's look at the properties here. Let's look at the SI unit. The SI unit for mass is kg, and the SI unit for weight, which is a type of force, and the SI unit for force is kg meter per second square. And also this kg meter per second square can also be denoted by big N. It's called a Newton here. So if we want to represent the mass here, we can say 100 kg of potato. That will be the correct way to say to refer to the mass here. In order to refer to the weight here, we should say 100 Newton of potato. Alright, or 100 kilogram meter per second square of potato. That is what we are referring to the weight here. Or people, in short, we can use 100 kgf, so kilogram force. So we can use kgf or this for referring to the weight here. So if you look at the previous confusion here of 1 kg of rice, does it refers to the mass or weight? Yes, it refers to the mass here, because kg is the SI unit for mass here, technically. But if you go to the market and ask the shopkeeper for 1 kg of rice, the shopkeeper always give you 1 kg of rice in terms of weight here, because they use the weighing machine here. So the thing is that they measure the weighing machine the shopkeeper use is it measure in terms of weight here, and the device is measured in this kgf unit here. So 1 kgf of rice. But the shopkeeper never tells 1 kgf of rice. Alright, they don't put the word F because nobody puts the word F here. People always use 1 kg of rice instead of putting F here. Technically it's wrong, and we are saying it wrong when we comes in measuring the weight here. Technically we say the unit's wrong, but people always use it anyway for simpler terms, for their comfort, for our comfort here. Alright, so you want to know the difference here and the context here also. it goes for the same with the measuring the weight of our body here. If I weight about 100 kg, you see here we always say in terms of 100 kg or things like that. We measure our weight here. So technically it's wrong to say the weight is 100 kg because kg is the unit for mass. But if you want to be technically correct, then we should always use the weight formula, and here the mass is 100 kg, so times the acceleration due to gravity here on Earth is 9.8 meter per second square, so that will give us about 918 Newton here. So to be technically correct, we should say I weigh about 918 Newton, but it's not. We don't say 980 Newton, we just use the word kg here, so it's better for people to understand. Everybody use kg instead of using Newton here. So those are the contexts you want to know and not to get confused. Technically we are saying it wrong, but for the simplicity, for the comfy of our own society, we use these units here. Alright, so I hope you get it. Alright, but let's take a look at some machine on how to measure the mass and weight here. As you can see in the picture, the machines used for measuring the mass are known as the balance, and the machine used for measuring the weight are known as the scale. So in the market, the shopkeeper always used the scale for measuring the amount of products here. Alright, so also for the balance, you can see the balance, the two balance or the analytical balance, which is mostly used in the physics lab, and the two digital balance, analytical balance of course, but those are usually seen in the chemistry lab. Alright, for measuring the small amount of salt samples. Alright, things like that. For you can see in the scales, you've probably seen some of the machines here used in the market. So you get the idea from there. So there are two measuring systems or two types of machines. Those are the things you want to know, and you want to differentiate it also, because one measure the mass and the other measure the weight here. So that is how you get the proper units here for mass and weight here. Alright, so now let's take a look at the formula of the mass and the weight here. The formula for mass is force over acceleration, and the formula for weight is mass times the acceleration due to gravity. So I'll get you to explain these two terms. Let me just write down here clearly. So for mass is equal to force by acceleration, and for weight is mass times acceleration due to gravity. So I'll get you to explain this here. Alright, so if you have remember in your lower classes, you might have studied that the force is equal to mass times acceleration, ma, right? So if you still remember this, it's good. If you don't, just keep on following me. Alright, so we know that we can just put the acceleration down here for mass, and we can get something like this. So we can also rearrange this formula in this one. So this is where mass gets its definition from. Alright, so you get the formula of the mass here. And for the weight here, so using the first formula here, that we know that force is mass times the acceleration. And weight is not any type of force. Weight is just a type of force. So we can just put here, since it is a force, we can just replace the F with the blue, which represents the weight here, and put the mass here times acceleration. But this is not any kind of acceleration, but this is acceleration due to gravity for weight. So we denoted by G here. Alright, so acceleration due to gravity differs from planets to planets. Alright, so as here on Earth, the acceleration due to gravity, let me just write down here. This G is called the acceleration due to gravity. Alright, so here on Earth, this value is 9.8 meter per second square. on the moon, this G on the moon, let's say on the moon, this is for Earth, it is 9.8 meter per second square. The G is on the moon, the acceleration due to gravity is about 1.6 meter per second square, and things like that. For different planets it's gonna differ. All right, but you get the idea. So you just change it, the notation here, and you get the formula for weight here. All right, so that's how the formulas goes. Very simple. So let's take a look at the first one here. Mass of a body is constant. So it means the mass of a body does not change, or it remains the same wherever the body is or the object is. All right, so take for example this guy here on the Earth and in the moon, the mass will be the same because the number of atoms or the amount of substance is not going to change even though he goes to the moon while he was in here at first. All right, but the weight here, it changes from place to place. And let me just show you the picture here of this astronaut here on the Earth and the moon here. So the mass here, the astronaut weighs about 100 kg, which is the mass, and on the moon it also mass the exact same amount here, 100 kg here on the moon also. But if you take a look at the weight here, it is 918 Newton. And then if you go to the moon here, let's just calculate that with the formula here. All right, let's just calculate the weight here for the Earth and the moon here. All right, so weight is mass times acceleration. On the Earth, which is, he weighs about, the mass is 100 kg. All right, so 100 kg times, here on the Earth is 9.8 meter per second square. So it will be 918 Newton. So this is on Earth, 980 Newton. On the moon, which is this here, 100 kg again, and the acceleration due to gravity on the moon is about 1.6 meter per second square. So if you calculate this, you get about 160 Newton here. So you can see the difference. The weight changes from place to place because it depends on the gravity here. So these are the things you want to know. The mass does not change wherever it is because it's just the amount of the substance. Amount of the substance is not going to change. All right, but the weight is going to change from place to place. So that's it. That's you have the mass and the weight here. I hope you get the understanding of the mass and weight here. All right, lastly, let's talk a little bit more on this mass here, which is the amount of substance. But it's a little bit more complicated than we think if we take this into practical for measurement here. And also scientists struggle to understand what exactly 1 kilogram is all about. Okay, so I'll get you to understand the story here. Alright, so let's say we have 1 kg of gold, 1 kg of iron, or 1 kg of copper. So as you can see, all of them exactly mass the same, that is 1 kg, but they have different number of atoms. So the number of atoms present here in this gold is going to be different from the number of atoms present here in iron. And not just that, the types of substance they have is different. So take for example, let's say if we keep the iron for a very long period of time, it can get rust. Alright, so this iron can get rust if we keep it for a very long period of time, and it's gonna lose its number of atoms here. The amount of substance or the number of atoms is gonna decrease because of rust here. We know that. And 1 kg in the meanwhile is always not gonna be 1 kg for this iron here because it loses number of atoms here. So it may decrease or it may gain based on the oxidation here, but you get the idea. The 1 kg is not always going to be the 1 kg. So it's for copper or gold or for any other substances. It always changes when it is kept for a very long period of time, or it is exposed in the air or things like that. So scientists have to come up with a point of reference here, and in such a way that they have to build something which does not change in kg, or they preserve it properly so that they have a point of reference for measuring things here. So they build an alloy called the platinum iridium alloy. platinum iridium alloy, which exactly mass 1 kg here, I'll show you in the picture here, but something like this. This particular alloy here, platinum iridium alloy, is kept in an artificial jar to preserve in order to avoid contacting with other substances from the air here. So this was established in 1889 during the weight and measurement conference in France, which is the headquarters here. Alright, so this particular alloy is also known as the standard international prototype of this 1 kg here. So 1 kg is defined as this particular platinum iridium here. Alright, so this is stored in France, and since scientists have already been established this, they have built this material, they make copies of this for the rest of the world. So they can make copies of this particular alloy, and they can send it to the rest of the world here. So let's say India gets one, let's say USA gets one, let's say Korea gets one, and every of the countries is gonna get a copy of this. Alright, so and the engineers or the industrial people, they come and they will calibrate their machines. They will calibrate the balance, the machine they use for balance, or the scales. They will calibrate using this reference point here. So they will calibrate their machine using this particular alloy here, which is exactly 1 kg. Alright, so it does not change for a long period of time. So everybody, the point is to ensure that everybody is using exactly the same amount of substance here, or exactly using the accurate mass here, that 1 kg is 1 kg and or it's not any other quantity here. Alright, you get the idea here. Or else if they don't use this and they use iron instead, which get rust, there will be a major problem there, right? So if they're calibrating their machine with those iron, then 1 kg here in India might not be 1 kg in the Korea, and so on. So all right, so that is the idea on where they have to create a point of reference here. All right, so before this, the people use 1 liter. Before this, people use 1 liter and keeping the 1 liter of water, of pure water, so to say, of pure water at 4 degrees Celsius. 4 degrees Celsius. Keeping this particular 1 liter at 4 degrees Celsius weighs mass exactly 1 kg. So people have used this instead of this in the earlier times. Alright, so this goes back, but this was not efficient. The amount of water gets evaporated sometimes, and this does not represent the quality of 1 kg here. So scientists have built a new one, but this new one is also changing. It's changing in a very small amount. So the number of atoms here is changing. The mass is changing. By now it's 2020 and people have already detected much amount of this change in here. So scientists now says that this cannot be defined as 1 kg anymore, and they have to search for a new standard here. So take a look at your reference standard here from your textbook here. You can see that scientists are in search of new standards for mass. This is the reason, because this particular platinum iridium alloy is changing in its mass. Alright, it's changing. So they have to search for new ones. Alright, so take a look at the YouTube here. You can search and get some ideas here. Feel free to search and things like that. But guess what? They have to search for a new one for this. So 1 kg, they have to redefine the new one here. Alright, so that's it for mass and weight here. Hope you learned something from here. If you have any doubts, comment in below. I'll get you to see that. As you can see, we have already seen that how mass can be really complicated, as it is the amount of substance. We have seen that 1 kg of different substance will have different amount of number of atoms here, which gets really complicated. So in order to make easier in chemistry, there's a concept called the mole, which exactly defines all of this number of atoms and the amount of substance here, which is called the mole here. So we will discuss the concept of mole in the next video lesson.